right, so let's talk about some infinite limits. We are going to talk about the word parts of infinite limits. We're not going to do any problems. We'll do that in class. So the definition of an infinite limit, we are to let f be a function that is defined at every real number in some open interval containing c except possibly at c itself. So here is a very important phrase that is saying that the function f is going to be a continuous function everywhere except at c. So the statement, the limit as x approaches c of f of x equals infinity, and we've talked about this before. This is talking about the limit not existing because it's increasing without bound. This means that for each m greater than 0, so any positive m, and they want m to end up being able to be a very, very large number, there exists a delta greater than 0. Remember, delta is the distance from c on the x-axis, such that f of x is greater than m whenever the 0 is less than the absolute value of x minus c is less than delta. Excuse me. So f of x is greater than m. Remember, we're picking an x in the interval of delta, and we want x to get closer to c. So whenever we have f of x, it's always going to be greater than m. M is a number we pick on the y-axis. And whenever 0 is less than the absolute value of x minus c, the first half of this says that x, the x that we pick, is not going to be c. So the distance between x and c is always going to be greater than 0. And the second half says that the distance between x and c is always going to be less than delta. So the x that we pick is always going to be within delta of c. So let's give this a picture. Here we have some function, and we have an m value right here, and we can move this m value around, except the m doesn't stick with the line. Worry about that later. So what we're doing, this distance from the asymptote right here to this line is going to be our delta. And same thing on this side, since distance is always going to be the same. We would be adding delta to c to get to this point, and subtracting it to get to this point over here. So what we're doing is we're picking an x on the x-axis. So let's do that right now. Let's create some point on the x-axis right there, and let's call this x. And now we're going to see where that maps to on the function. So we're going from here through this point, and let's make this line a little bit bigger. Okay, so this point right there is the intersection point. So whenever this x is going to be this x, give me the point line axis. I want the point. Yes, the point. Whenever this point is between delta of c, is within delta of c, this f of x up here is going to be greater than m. Okay, well, let's make m bigger than delta, or m bigger than f of x. Okay, well, we did that, but now the x value that we had picked is not within delta. So if we put it within delta, you can see the point goes off the screen, and we can actually, let's find that point away up here. It is still greater than our m value. Okay, so what this is saying is that whatever delta we pick, there is always going to be a, whatever delta we pick, or whatever x we pick within delta of c, there is always going to be an f of x greater than whatever m is. Okay, so and that is this picture right here. So definition of infinite limits, we can have a negative limit, or a negative infinite limit. All this is saying is that the limit as x approaches c of f of x equals negative infinity, means that it the limit does not exist because the function decreases without bounds. And so for each n less than 0, so n is always going to be negative. It can be a very, very negative, or very small negative number, or very large negative number, however you want to think of that. There's going to exist a delta greater than 0. Delta means the same thing, such that the function for whatever x we pick is always going to be less than n whenever x is not, or the x that we pick is not c, so it's always going to be greater than 0. and it is always going to be the distance between x and c is always going to be within delta. So let's look at another picture. Here we have another function, and so we have our deltas, and here's our n value, and so whatever x we pick between c and our delta boundary is always going to give us a f of x that is going to be less than n. No matter how far I put n down, there's always going to be another part of the graph that is going to be, I should say, for whichever x we pick within delta and c, within delta of c, there's going to be an f of x that is greater than what our n value is. So, where are we? Those are the definitions of infinite limits. Pretty self-explanatory. We've gone through that already. The definition of an infinite limit. So these are directional. To define the infinite limit from the left, instead of saying 0 is less than the absolute value of x minus c is less than delta, then we can say that c minus delta is going to be less than x is less than c. So let's use the positive infinity to look at this. We'll bring this all the way back down, give us some room to work. And we're actually going to get rid of x, if I can, maybe, let's see. This line, delete it. There, okay. So the definition is saying that as 0 is less than the absolute value of x minus c is less than delta, we're looking at the infinite limit from the left. So we can replace it with x minus delta is less than x is less than c. Or, I'm sorry, c minus delta is less than x less than c. So c minus delta is talking about the distance on this side. And remember, c minus delta is always going to be, or it should be, a very small number. So c minus delta will give you a positive number. And so x, that is always going to be less than x. All that says is that x is going to be within delta of c. X is always going to be in here. If we were looking at something on the negative side of the axis, both those numbers would be negative, but they would still, their comparison would still hold true, that x is always going to be greater than c minus delta. And c is always going to be greater than both of those quantities. So this is just setting up order, that the x coordinate of this point will be given by c minus delta. X is always going to be in here, and c is always going to be the largest one. So that would be the definition for the infinite limit from the left. Similarly, the infinite limit from the right, this c plus delta will be here. X will always be in between c and delta, and c is always going to be the smallest value. So looking at this right here, c is the smallest, then comes x, and then c plus delta will always be the biggest one. Vertical asymptotes. If f of x approaches infinity or negative infinity, as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph x. Let's give that. Let's talk about this for a second. Basically what's happening is whatever makes the function undefined. And I think we'll get into that later. So that's the definition of a vertical asymptote. Is wherever graphically, let's say this is the graphical definition of a vertical asymptote, that if f of x approaches infinity or negative infinity, like it's doing here and here, playing with these pictures, as x approaches c from the left to the right, this is the line, this vertical line right here is the line x equals c. That is going to be the vertical asymptote of the graph f. Finding vertical asymptotes, let f and g be continuous on an open interval containing c. It contains c. But if f of c does not equal 0 and g of c does equal 0, and there exists an open interval containing c such that g of x does not equal 0 for all x not equaling c in the interval, then the graph of the function given by h of x equals f of x over g of x has the vertical asymptote at x equals c. That's a lot of words. Let's simplify it. If you have a rational function meaning you have some function divided by another function, and the x value that makes the numerator not 0, that's this piece right here. If f of c does not equal 0, the numerator is not 0, and the denominator is 0, that means g of c is 0, this g of c down here. So the numerator is not 0, the denominator is 0. That is going to be where there's going to be a vertical asymptote. This extra part down here, there exists an open interval containing c such that g of x not equals 0 for x not equaling c. All that is saying is that whenever we are looking at this function, something like this, is that the function does exist up until the asymptote. This bunch of words right here, such that g of x does not equal 0 for all x not equaling c. So the function does not equal 0 whenever the x value that we are picking does not equal this c value right in the middle. And so that's simplified, the place where there's going to be a vertical asymptote. So looking at this example right here, it's pretty easy to see that the function that this is going to be undefined at x equals 2. So just for kicks, let's graph this. Let's see what happens. Let's get ourselves a new page that will be a graphs page, and let's make this function. It was 4x over 4 minus x squared. We have the function of 4x over 4 minus x squared. And when we graph this, there's a lot of stuff here. So we were saying that the function where x equals 2, there's going to be vertical asymptote, but we forgot about negative 2. Negative 2 also works. So whatever makes the denominator 0 and the numerator not 0, that is going to be where there are asymptotes. So that is infinite limits in a nutshell. There's another problem. And there are a bunch of properties. If the limit is x approaches c, if f of x equals infinity and g of x is not infinity, so g of x is continuous at c, and that should be an arrow, and f of x is the limit does not exist for f of x at c because it is an infinite limit. If you add the two functions together, you're going to get an infinite limit. If you multiply them, you're also going to get an infinite limit as long as our x is positive, and it will be a negative infinite limit as if x is negative. And if our g of x, our continuous function at c, is being divided by an infinite limit, the limit will actually be 0. Similar properties hold for one-sided limits and for functions for which the limit of f of x as x approaches c is negative infinity. So instead of this being positive infinity, it would be negative infinity, which would make this negative infinity, this negative infinity, this positive infinity, this stays 0. And like we said, they are the properties hold for one-sided limits also. All right, sounds good to me.